Welcome to our webinar on thermal characterization of heat transfer fluids for data center cooling. This is a special guest webinar where we will be joined, where I'll be joined here shortly by two individuals who've contributed to the work in today's session. C-Therm provided the thermal conductivity and heat capacity data that we'll be going over here today. Wasif Altaf, who's an application specialist from the Center for Industrial Rheology. He will be joining secondly to go over some of the physical property characterizations. And then lastly, the materials were provided by Soltex. Bret Timme will be joining. He is an electrical engineer from Soltex to talk about what all of this data comes together as, what the products look like in terms of their material performance. So should be a good one here. We're going to get into it right now. So really, as we're going through this, trying to design the content for the session, who is this information really geared for? Are we trying to really, target in what we're presenting? And there's a few different areas. Whether you're, someone in charge of selecting the materials that are going to go into different thermal management systems, maybe you're a dedicated high performance computing engineer working specifically with data centers, or more on the chemistry R&D side of the formulation development. This information presented herein will be touching on what we think is some very important aspects in all of these different areas. And that being said, when we do these like application specific webinars, it's always good to kind of take a step back and be like, why is this something that we're talking about? Why do people care about it? And I found this stat from Goldman Sachs this year, kind of stating just the sheer amount of capital being introduced into this space. Trillions of dollars are going into the overall computing power, the data center infrastructures, power consumption considerations. So clearly there is, a lot of work and a lot of research being done in this space. There are a variety of other aspects to consider, but, one of the big things, of course, it's a big driver for a lot of businesses out there, is the financial aspect. So this is clearly an area where a significant amount of work is being put into. So let's talk about it. So before we get into it, I just wanted to give a quick background introduction to C-Therm for those that may be unfamiliar or newer to us. So C-Therm, we focus on the thermal conductivity side of things. We develop instrumentation, specializing in the transient space for the non-destructive measurement of varying materials. So everything from solids to liquids, powders, pastes, low conductivity to high conductivity. Really, if thermal considerations and thermal conductivity is important to you, this is an area that we support a lot of researchers and companies in their development. Speaking of, just wanted to flag a few of our groups that we've worked with, our testimonials. One that I wanted to share here was from Dr. Mina Alina Adriana, who is a researcher at the Technical University of George Asahi Lassie, kind of commenting on how she's happy with the Trident system, being able to cite the equipment in the different papers and published works. It has been a reliable and valuable tool in their research. So, just wanted to share that quick story. If you're interested to hearing about what other folks have to say about their experiences working with us here at C-Therm, feel free to check out the QR code, which leads to the testimonials page on our website. Now, in terms of an agenda for us here today, I'm kicking things off with, again, a little bit of an introduction and some kind of highlighting some of the challenges in fluid-based measurements. I'll introduce the C-Therm Trident platform, which is what was used for the measurements from C-Therm side, go over some of the thermal conductivity and heat capacity data that was collected, and then I'll be handing it over to Wasif to go over some of those physical properties that were characterized. And lastly, Bret will be joining to kind of round out the session, talking about some of the, what this information really means, giving a little bit more context to the application space and the materials that are being used. And again, we'll wrap things up with a Q&A. So, starting out, liquid cooling and the figure of merit. Couple things we wanted to just quickly introduce to essentially set the stage for today's chat. If you're working in this space, traditional air cooling solutions have existed for many years. They are, fundamentally designed to move heat through that through air-based movement. These systems, while good, are starting to run into some bottlenecks. You get additional considerations around fan, like the noise level, the overall bulkiness of some of these systems, and of course, the space, because space as a commodity in and of itself is something really important to consider. So of course, we're talking more about the liquid cooling. This specifically, whether it's liquid plate cooling, immersion cooling technologies, these systems by design can vary, but the singular kind of commonality here is that the liquid media, the heat transfer fluid that is used, is going to be a dominating performance factor in how well these systems work. So essentially, being able to quantify their performance becomes an important aspect, not only to just this overall system design, but for budgeting on the type of other components that need to be built into these systems, the performance levels, etc. And this brings us to the description of the figure of merit. This is something that we wanted to talk about specifically here today because the figure of merit isn't simply one property measurement. It actually brings 5 aspects of material performance into one unified physics grounded index that really allows for a nice holistic approach to the characterization of materials. Of course, individually, each one of those properties is important. However, being able to take this more fully well-rounded approach gives you the ability to really identify which sample is truly going to perform not only on the thermal side of things, but you take into consideration, the pumps that have to move the fluids around, what happens in terms of when they are exposed to temperature, how their physical and thermal properties change. This is what we're going to be really kind of centralizing all of the performance rankings around here today. And of course, that's why C-Therm, we provided the thermal data, and Wasif will be taking us through the data characterized at the Center for Industrial Rheology. So wanted to take a quick second here, take a little pause. I wanted to put a quick poll up and maybe get the audience to give maybe 20, 30 seconds. Just wanted to take a quick look on, if this is a space that you are, working in right now, if it's something that is very new to you, maybe you don't have much experience in this space. Yeah, just take a few minutes, just kind of see where people are at in terms of what properties they're measuring. And of course, the great point for us here today is if you're measuring some but not others, this would be a great opportunity to be able to reach out to either myself or Wasif or Bret with any specific questions. We'd be certainly happy to guide you towards appropriate method choices. All right, I'll let it go for another maybe 5 or 10 seconds or so, give everyone a chance to answer. All right, well, let's take a look here together. So I'll share the results with everyone so we can kind of see what folks are working in. So yeah, quite a mixed bag. I see thermal conductivity being one of the primary measurements, which nice to see. But all properties Some folks currently not measuring any. So of course, if this is something that you're looking to get into, I'd say you've come to the right place to get some good information on what those options look like. So thank you everyone for your participation. I'll go ahead and stop sharing that poll right now, and we'll continue on. So what are the challenges? Because with any application, of course, there are things to consider. And from the thermal side of things, I wanted to chat a little bit around why, in some cases, liquids introduce their own unique issues in terms of measurement compared to more kind of standardized bulk solid samples. And this really centers I'd say the number one area, or the number one reason where liquids data goes wrong, is when you get convection. In an ideal setup, your thermal conductivity measurement is doing just that. It's measuring thermal conductivity. But if convection forms within your system, this is something that is going to introduce a measurement bias. Any form of heat transfer, not solely through conduction, will result in some mismatches in terms of the accuracy. So there has to be ways to mitigate this. Generally speaking, using a shorter duration test, limiting your sample volume, the duration, so shorter duration and lower power inputs. So the amount of total thermal input that is used, keeping that on the low end, are some very common approaches, but not all methods fundamentally, let's say, provide that. So method selection becomes important. And it's something that we'll talk about and why we chose our specific method here today for the testing of the work that we did. The other aspect is the fact that these properties can vary under different conditions. So specifically looking at temperature here today, all materials, some are more stable than others, but understanding how your material performs in your desired operating window is really important, because if you just, let's say, assumed performance of the at room temperature, and it's going to be that way through your entire temperature profile range, that's going to lead to some issues down the line. So we wanted to talk about that here today. So the data that we'll be presenting was across a defined temperature range, where you see some common similar systems functioning. And lastly, and this is really, I'd say, a kind of a nod to the transient-based approaches, is the ability to deal with sample volume constraints, throughput pressures, and again, representative testing conditions. These different aspects are all very much, I'd say, factors that transient methods handle very well. Generally speaking here, our sample volume requirements are for liquids, we'll say in the milliliter range. Some of our methods as low as 2 to 3 milliliters, upwards of maybe 60 to 80 milliliters, depending on which option is used. Your throughput. So in an R&D environment, a big challenge, of course, is, especially if you're a formulator and you're trying to iterate and design different materials, how do you know if your tweaks are improving or detracting from your end properties? So being able to rapidly test materials, the total test times becomes an important aspect to consider. And then lastly, the representative testing conditions. So being able to test under, as I said, like, for example, the temperature range becomes something quite important in really getting, I think I said in one of the slides earlier, apples to apples comparisons across the materials range. So this brings us to our Trident instrument. Wanted to quickly introduce this. So Trident was developed as a modular platform. It brings together 4 different methods for thermal conductivity and related property characterization. Of the 4, we're not going to go into all of them here today. What we will do is kind of take a look. And part of the idea here is that in many cases, you do need multiple approaches to handle the variety of samples. This quote from Abraham Maslow kind of embodies the idea behind Trident. When all you have is a hammer, everything looks like a nail. So, one of the issues that we see is in some aspects, being able to choose the most appropriate method is very important. Of course, here for us today, we're going to be going into that. But if you wanted to learn a little bit more, we do have this free method selection guide. It's available as a free download. It goes over all of the different options that we have on Trident and gives some nice context to, what applications are they commonly used for, what samples are typically selected for the different methods, and so on and so forth. But yeah, going into the data that we collected here today. So looking first off at thermal conductivity and then specific heat capacity. So for us, we measured all of the samples here using the transient hot wire. So this method is a really great option for the testing of liquids because of its short test times. The ASTM standard for the hot wire is one that is commonly referenced. Historically used for like traditional ICE combustion engine coolants and fluids testing. We've seen this adopted into many groups that are doing like EV development, and of course here now in the AI data center space. So the data that we're going to go over is 4 samples, all of which were provided by Soltex. There's 2 competitor samples, a new and a used, as well as 2 samples from Soltex, their optical CM and optical PE. So of course, thermal conductivity, and then we did the heat capacity measurements internally here using a DSC. So wanted to quickly just jump right into the results. And as we kind of see on screen, there were some similarities across these samples in that there was a relatively consistent value for, with minimal difference, especially when looking at the room temperature values, like where they started at. All of the samples exhibited a net decrease as a function of temperature. From room temp to 70C. Now, the largest shift in that total decrease was about 4.2% compared to room temp. So interestingly, with all of these samples, there is fairly consistent results across the temperature range. It's an interesting thing to point out in that if you were to look solely at the thermal conductivity side of things, you may assume that, well, all these materials are effectively performing within a few percent of each other. So what's the big deal? Why would I need to really kind of do anything else, or any of these will work, right? But let's take a look at where we're starting to see some other properties and where some of these differences start to develop. One of the notable ones here from the thermal side was when we actually looked at the CP values. We noticed 2 different groupings. Generally speaking, heat capacity rose as a function of temperature, but we saw the new sample, that was the competitor sample, and both the Soltex materials had a fairly like tighter grouping between that 2.25 and 2.5 joules per gram Kelvin, whereas the used sample had a notably higher CP value, kind of, again, following a similar trend. But once we start to see like where some of these materials behave similarly and then where some of these start to behave differently, you can get an idea that once we get to the FOM calculations, how this can start to introduce shifts in what is really the holistic performance of some of these samples. So that being said, at this point, I'll be handing it over to Wasif to take us through some of those physical property measurements that were done. So I'm going to stop sharing here. Wasif, feel free to take over at this point.
Thank you very much, Aria. So, as Aria mentioned, I'm going to be going over some physical property characterization and in terms of the properties that we've measured here at the Center for Industrial Rheology. Just as a quick introduction to myself, my name is Wasif Altaf, application specialist at the Center for Industrial Rheology. My role mainly involves exploring many of the different applications of our analytical capabilities across the many industries that we work with, which is what brought me into this particular topic. In terms of who we are as a company, the Centre for Industrial Rheology is a specialist materials analysis lab, and we provide rapid access to essential materials insights with our capabilities spanning obviously rheology, as the name suggests, but also a lot of associated areas. So we're looking into thermal properties, interfacial, foaming, and even other areas such as tribology, powder flow, texture, and even particle analysis. Just to give you a taste of who we work with a range of different companies across a wide range of sectors, including advanced materials, pharmaceuticals, cosmetics, food and drink. And this is an overview of some of the key companies that we've worked with in the advanced materials sector. And across all of these industries, I like to think that the main reasons why a lot of these companies continue to work with us is due to our unique combination of our breadth of experience, our extensive list of capabilities, and the support that we offer. We ensure that you get the most out of the data that we do provide to you. And overall, we like to see ourselves as a partner in materials characterization. So that was just a bit of background about us as a company. Now, in terms of what I'm going to be talking to you about today, as Arya mentioned, we're going to be continuing to discuss the properties related to the freedom of merit calculations. On our side, we measured dynamic viscosity, density, we calculated the coefficient of thermal expansion, and those are all properties required for the FOM calculations. But we also looked at surface tension, which isn't part of the freedom of merit scope, but it's rather an interesting extension, which we are going to get into. So starting with viscosity, I just want to give a little bit of context on how we actually measured this before I jump straight into the data, because this may be a little bit different to what some of you might be used to seeing in this space. Now, generally, viscosity for any low viscosity ideal liquids, with ideal liquids being liquids where your viscosity does not change based on the shear that's applied, they tend to be measured using something like a glass capillary viscometer that you can see here on the left. And with those, you're essentially timing how long it takes a fluid to drain through a tube under gravity, and that gives you a kinematic viscosity value. With this method, temperature control and equilibration can sometimes be a little bit tricky, and there can sometimes also be some variability between analysts if you're just using this method alone. What we used in this study is a rotational rheometer. It's one of our 5 rotational rheometers that we have in the lab. Specifically, we used a TA Instruments DHR2. And the basic principle of a rheometer is that it delivers torque to a geometry and measures the resulting deformation in the sample. For anyone that's more familiar with rheometers in terms of the geometry used for these measurements, we used a 2-degree cone. However, we do have the ability to adapt the geometry depending on the viscosity of the fluid. So for example, in some cases, a concentric cylinder may be more appropriate. I think some key benefits of a rheometer are worth mentioning. So small sample volumes, you only need about a milliliter to conduct measurements. And I think most importantly for this application, it has the ability to step through multiple temperatures quite accurately due to its Peltier plate technology. Underneath on the bottom plate, we have a Peltier plate, which provides that temperature control. So to the data itself now, we measured viscosity at 6 different temperatures, at the same different temperatures that Ari has mentioned that was carried out for thermal conductivity and specific heat capacity, relevant to what these fluids would be sort of experiencing in an immersion tank. And we conducted 2 runs at each temperature. And the trend that we see here is exactly what physics would tell you to expect. Your viscosity decreases as temperature increases. In terms of the differences between the samples, we can see that the optical CM sample sits at the top of the viscosity range, whereas optical PE has the lowest viscosity. And in terms of the competitor fluid, you can see it sits in between those 2 samples, and there's no meaningful differences between the fresh and the aged samples that we see with the viscosity values. Now, for freedom of merit 1, viscosity is going to primarily influence how readily the fluid circulates thermally. However, beyond freedom of merit 1, viscosity data is practically useful in a couple ways. For any engineers that are present that are used to designing pumps, if you've got a forced convection system, they need to be designed to overcome any pressure drop to actually push that liquid through. So viscosity data feeds directly into pressure drop calculations, which also affects things like pump sizing and energy consumption. And this is going to be related to freedom of merit 3, which Bret will go into further later. Moving on to density now. We used a density meter utilizing the oscillating YouTube method. Simply the way this works is that we have a small sample of small sort of volume of fluid. We're talking less than a milliliter in this case, and we draw that into a hollow U-shaped tube, which is then set into mechanical oscillation using the pulse excitation method. Now, the key principle here is that the frequency at which that tube oscillates depends on its mass. And since the volume of the fluid inside is fixed and it's known, the instrument can then calculate the density directly from that oscillation frequency. It's quite a fast, precise measurement. And as the tube itself is thermostated, it's quite good for precise temperature control, again, allowing us to get density over a range of different temperatures. And again, with viscosity, 2 runs per sample at each temperature was done here. And looking at the results, the pattern is going to be as expected. You get a steady linear decrease in density as you increase your temperature. As you're warming up your fluid, it expands and the same mass now occupies a slightly larger volume, so the density drops. In terms of the differences between the samples, optical CM had the highest density we can see across this whole temperature range, and the other samples sat below it. And again, as with the viscosity data, there was no meaningful differences between the fresh and in-service competitor products. Now, beyond being a value required for freedom of merit calculations, we also used it to feed directly into the coefficient of thermal expansion calculations, which we're going to come on to next. But density has further practical relevance too. It feeds into things like tank design, as a denser fluid means a heavier filled tank, and also feeds into things like pump design, as if the fluid is pumped from the bottom of the tank, it has to work against the full height of the liquid above it. So for the coefficient of thermal expansion, as mentioned, we derived it from the density data that we just looked at using the equation shown here on the right. The coefficient is calculated from a pair of density measurements at 2 different temperatures. And the basic principle here is that if you know how much a fluid's density changes between 2 temperatures, you can figure out how much it's thermally expanding. Now, rather than selecting one temperature pair, say 25 and 70 degrees C, and calculating a single value from that, we computed the coefficient for every possible pairwise combination of our 6 temperatures, and that gives us 15 pairwise calculations per sample, which is just more statistically robust. We then applied a Tukey interquartile range filter to those values before taking the mean as a standard outlier detection method, and in this case, there were no outliers identified. And in terms of the results here, we can see that the optical PE sample showed the highest coefficient of thermal expansion, and optical CM had the lowest coefficient of thermal expansion. And physically, what the coefficient of thermal expansion is capturing relevant to the freedom of merit calculations is that a fluid which expands more when heated will generate a stronger density gradient near those hot components. And that's what's going to drive any buoyancy-driven circulation in any natural convection systems. Now, that covers everything regarding the freedom of merit properties that we've measured on our side. But I'm going to talk a little bit about surface tension. So for surface tension, it's not included in any freedom of merit calculations, and rightly so. It's not going to contribute directly in any of the heat transfer calculations either. But as we have a lot of analytical capabilities in our lab, we decided to just investigate this property to see if it would reveal any interesting insights. So we measured this using a pendant drop analysis, and this is essentially where you just extrude a droplet from a needle, you capture the image of that droplet, and you use the Young-Laplace equation to resolve this into a surface tension value. Now, this was only done at ambient temperature, 2 runs again. And we can see here that with the competitor product, between the fresh and the in-service samples, we've seen that the bulk properties of viscosity and density remained largely unchanged. However, we can see that surface tension has dropped quite measurably. So this could be consistent with things like degradation products forming during service and accumulating at that interface, acting to reduce the surface tension there. So potentially highlights the usefulness of surface tension in any sort of monitoring of fluid health over time. Now, a lower surface tension is generally going to be preferable as it ensures the fluid wets the component surfaces completely. However, this does need to be considered alongside dielectric performance, which Bret will go into later as well. So if you can imagine, if the dielectric performance of the in-service competitor product was significantly worse, that surface tension improvement alone would not just make it the preferred fluid for a live system there. So that's everything from our side. If you're interested in carrying out any of the tests that we've covered today, or you want to find out more about our services or characterization capabilities, do feel free to get in touch. And if you have any questions regarding what we've just covered, as Aria mentioned, we do have a Q&A session at the end. I'll now hand over to Bret from Soltex to round up the discussion today.
Thank you, Wasif. Could you excuse me for one moment? Just trying to pull up my slideshow here. All right. Hello, everybody, and thank you for joining us today. My name is Bret Timme, and I'm an electrical engineer here at Soltex. I'm excited to talk to you about the thermal characterization of heat transfer fluids for data center cooling. And today I plan to cover mainly three things: the multi-property figure of merit approach that we use to characterize how well a fluid actually removes heat from a system, the products that Soltex manufactures to supply this fast emerging market, and a collaborative study we carried out with C-Therm Technologies in the Center of Industrial Rheology to put our fluids to the test. So, a quick introduction of Soltex. It's shorthand for Synthetic Oils and Lubricants of Texas. We were founded in 1990 in Houston, Texas, and we are still here today. Our production and testing is split between Baytown, Texas, and Belleville, Canada. Both are ISO 9001 registered facilities, which qualifies us as a manufacturer and distributor of organic chemical additives, electrical and lubricating oils, and oil-based formulations. For more than 30 years, we've grown into a leading provider of specialty chemical solutions, base stocks, additives, and functional end-user fluids, with a deep expertise in deep dielectric and thermal management fluids, quality control, research and development, and custom formulations. And we're excited to announce a newly constructed dielectric and thermal fluid blending facility in Baytown, Texas. It's shown in the second image on the slide. And we anticipated to be a part of what was going to end up supplying this emerging market of single-phase immersion cooling. This graphic just shows North America and our current locations. Our main office is in the Woodlands, Texas, and our blending facility that I just mentioned is just right out of Houston and Baytown. We have a warehouse located in California and Ohio for distribution, and another manufacturing and facility and lab in Belleville, Ontario. Here's a quick overview of our product portfolio. As you can see, it's fairly broad, but coming from an electrical background, my focus has been on the products designed to come into direct contact with electrical components. That includes dielectric and thermal fluids, transformer fluids, capacitor fluids, and single-phase immersion cooling fluids. While these products are closely related in their formulation and processing, today we'll focus on our optical fluid line formulated specifically for single-phase immersion cooling in data centers. And before we get into the testing data and just to set up some context, I wanted to set the stage on where single-phase immersion fits. The core idea is simple: to submerge high voltage electronics into a dielectric fluid bath that cools and electrically insulates them simultaneously. This broad cooling technology opens the door for a lot of different markets. Anywhere you have dense heat and sensitive electronics, single-phase immersion has a role. High performance computing, EV battery packs, grid scale energy storage, power electronics like inverters, converters, and competitive edge telecom sites where footprint and efficiency is highly constrained. But the applications driving the most urgency and demand today is the ones we'll focus on for the rest of this seminar, is AI data centers, where GPU racks now exceed 100 kilowatts each, well past the point where air cooling can keep up on its own. So let's take a look on why the demand is growing so fast. This chart shows the global data center electricity use in terawatt hours per year, and the trajectory that we can anticipate consumption is set to be more than doubled by 2030, from about 415 terawatts in 2024 to 945 by the end of the decade. And the driver behind this curve is AI. Power for AI accelerated servers is growing around 30% per year, compared to about 9% for conventional servers. But the part that matters the most for us is roughly 60% of the energy that the data center is demanding is consumed by the servers themselves. And nearly every watt that is consumed by the server is going to have to be removed in the form of heat. So the total demand is doubling, but the bigger challenge isn't about the overall power consumption of the data center, but it's about how densely that power is packed into the data center. This is what I mean by density. The chart depicts the power of a single AI rack across NVIDIA's GPU's generations. We've gone from about 40 kilowatts per rack with the Hopper generation in 2022 to around 130 kilowatts per rack with the Blackwell today. Next year's Rubin generation pushes towards 200 kilowatts per rack, and it really starts to take off past that point. Rubin Ultra is expected to near around 600 kilowatts in the year 2027, and the Feynman generation points towards a full megawatt per rack around 2028. To put that in perspective, that's roughly a 16-fold jump in just a few years, an exponential growth trend from 8 kilowatt average rack back in 2020 to about 130 kilowatts per rack today, with an order of magnitude more in the not too distant future as well. Nearly all the power that is consumed by these server racks is going to be dissipated as heat, and it's all concentrated into a single footprint. So the question becomes, how do we get the heat out? Because not every cooling method can keep up with this projected demand of power consumption from the servers. So this depicts the different cooling technologies that are employed in systems today and that will be employed in future systems. Each bar is the approximate heat a given cooling technology can pull from a single rack. And the dashed line is today's densest AI rack's about 140, 130 kilowatts per rack. Air cooling tops around 30 kilowatts per rack, and it's currently being left behind with the next generations of servers. Cold plate or direct chip gets you to about 120 kilowatts per rack, but is essentially at its limit against today's technologies. This combined with embedded and microfluid cooling etching into the chips is sustaining today's workload, but it's hitting its limit. Immersion is where the headroom seems to be. Single phase handles around 200 kilowatts, and two phase approaches 250 kilowatts. Now, two phase is the most effective on paper, but it relies on fluorinated PFAS-based fluids that are expensive and face tightening regulation. So single phase immersion is not practical, scalable, so single phase is the practical and scalable workforce. And importantly, its ceiling is not fixed. As we improve formulations and improve base fluids and add packs, that ceiling can be lifted for single phase immersion as well. So the key insight for the rest of the talk is the performance of immersion cooling is gated by the fluid itself, which raises a question of how do you actually measure whether one fluid moves heat better than another? And that's the hope of the figure of merit, which is laid out by Open Compute Project. So how do we measure whether a fluid is actually good at moving heat? Not a single property measured as a part of this study entirely captures heat removal on its own. That's exactly the multi-property approach OpenCube Project took in their immersion fluid specification. Instead of chasing individual properties, they bundle them into a figure of merit. Each of the formulas that roll several properties into a single score and tell you how fast or how effective heat is removed. The first one, figure of merit 1, captures natural convection. Heat carried away by the fluid rising off the components on its own from a differential in the temperature and density, which produces a buoyancy force. There's not a pump involved. Higher is better. The spec sets two tiers, 35 and 45 at 25 degrees Celsius. OCP calls for this and is their recommended best real world indicator of performance. The figure of merit 2 is for forced convection, how the fluid performs once a pump pushes it through a system. Again, higher is better, with a threshold of 19 at 25 degrees Celsius. And FOM3 is just purely the viscosity, and it's flipped in the sense that lower viscosity fluids are preferred. And here is how our fluids combine with the data from C-Therm and the Center of Rheology, how they combine into FOM1 across the temperature range. As it relates to natural convection, the one that OCP calls the best real-world indicator, we measured 4 fluids across the operating range from 25 to 70 degrees Celsius and plotted them against the 2 specs at 35 and 45 degrees at 25 degrees Celsius. A couple of things that stand out. First, every fluid improves as the temperature rises. FOM1 climbs with temperature, which is exactly what you want since these systems typically operate around 40 degrees Celsius. Second, optical PE is the top of the line. It leads at every single temperature. It clears the tier 2 spec across all temperature ranges, while the others sit lower and it pulls away as the temperature rises. The 2 competitor samples land in the middle, and our second fluid, optical CM, comes below them here. On the metric that matters the most, optical PE is the strongest performer in the group, and we have the capacity to land a product anywhere that we want in between optical CM and DC, so we can cover the entire range and hit whatever our customers' specifications are. The lead of optical PE is even clearer when we line it up against the broader field from all the data that was collected in the first revision of the base fluid specification from OCP. We've taken the FOM1 measurements at 25 degrees Celsius and dropped our fluids from this study into the broader field from the first revision of OCP's white paper. At the top is optical PE. Out of all 15 single-phase fluids, it's the highest FOM1, edging on the best benchmark fluid and beating both competitor samples. The dashed lines are the 2 spec outliers, and you can see the optical PE clears tier 2 with room to spare. The margin at the very top is narrow. The top few fluids are clustered pretty closely, but the takeaway holds on the figure of merit. The OCP considers most representative of real-world cooling. 0.1 better is a small threshold, but we are at least in the top 3 fluids. This is the figure of merit that OCP expects to separate fluids the least, and our data shows exactly that. You'll notice the scale here is zoomed in, very little change as the temperature changes. All fluids sit in a narrow band between 32 and 35, and they stay fairly flat across all temperatures. The competitors use samples marginally on top, and our 2 optical fluids sit in the middle of the pack, essentially tied with the new competitor sample. But the numbers that really matter the most is but the number that really matters is the spec. FOM2 only needs to clear 19, and every one of these fluids beats that by a wide margin. They'll comfortably be above it. And this is actually consistent with OCP has said about FOM2. It's a leading check and not a screening tool. It assumes identical flow for every fluid, so it tends to be underrated the more viscous ones. And their words, FOM1 is the better differentiator, which is why our strongest separation shown up here is for FOM1, and we can confirm that by comparing our FOM2 data to every other fluid that was a part of the original study. And here's the figure of merit 2 ranked against every other fluid that was tested as part of OCP's first revision. 15 fluids ranked, and our fluids and the competitors' fluids are shown. Our competitor fluid is shown in red and yellow, and ours are shown in blue. So FOM2 just doesn't differentiate, which brings us back to the point that OCP makes about our own data confirmations. If you want to know which fluid truly moves you better, FOM1 and viscosity are our main candidates, and FOM3 is purely just viscosity. The first thing to make note of is for FOM1, the lower is better. A thinner fluid flows more easily through the dense fins of a heat sink and reaches the hot surfaces more efficiently, so it actually ends up cooling better. We've plotted in millipascal seconds across the same temperature range as before, and you can see with the dashed line that the spec is at 15, and that's for 25 degrees Celsius. For optical CM, you'll see the I'm sorry, let me start optical PE. And for the standout, it's optical PE, our bottom line, the least viscous fluid at every temperature, comfortably the best of the fluids that we tested. For optical CM, you'll see that it's the thickest fluid here at 25 degrees Celsius, but same philosophy as before. We're able to blend and meet any product within the range of the two. And notably, within the operating temperature range that we expect these systems to be in, optical CM's viscosity will be far below 15. Here's the viscosity at 25 degrees Celsius. All 15 fluids ranked. This time, the lowest is the highest since lower viscosity is correlated with better heat transfer. Optical PE is right near the top, third lowest of the entire field and the lowest of any of commercial fluids, beating both competitor samples comfortably. The two fluids ahead of it are unnamed benchmark fluids from the spec, and you can see the wide field really is a few of these fluids are 3 to 5 more viscous will pass the spec line. So across all these figures of merit, a clear picture starts to emerge. Optical PE leads on FOM1. It's amongst the lowest viscosity fluids on the market, and it clears every spec, which is exactly the combination that we were looking for when we formulated it. And this leads to what is our philosophy of formulation and what do we need to think about when trying to formulate better fluids beyond this. The main lever for formulating this sort of product is viscosity. It's the single most powerful variable we have. Once we drive it down, we can raise the heat transfer and lower pressure drop at the same time. But you can't chase low viscosity on its own blindly, and our data is able to show why. The used competitor sample actually posted higher thermal scores than when it was new. The reason is because it had absorbed a lot of water in service, and the water nudged up its specific heat capacity, but at the same time took away from the fluid's dielectric integrity. And that's the trade-off that you can expect to see in a fluid that's in service. It may get more effective at heat transfer, but is going to sacrifice its dielectric integrity in order to do that. Secondly, we want to formulate for the full service life, not just a brand new fluid on day one. Properties shift as the fluid ages, so does stability, oxidation resistance, and keeping water out of what matters most over the years of operation. Lastly, we want to optimize for what actually matters. And from what we're able to tell, FOM1 and viscosity are the best figures of merit evaluated across ideal or operating temperature ranges. That balance of a strong, stable thermal performance without compromising dielectric integrity is exactly what we've engineered the optical line to achieve. And what this collaboration with C-Therm in the century of radiology has allowed us to prove. And with all of that, I will open up for questions. Thank you all for y'all's time.
Awesome. Thanks, Brett.
Yeah.
Yeah, folks. So just going to just wrap things up here, leading into the Q&A. So, I know we're at the top of the hour. So I did see a question or two pop in. So if you do have any questions, please feel free to type those into us. Just a few kind of closing out notes from us here. Of course, if you're looking for additional information related to resources, past webinars, or even information on today's topic, definitely feel free to check out the website. There's a lot of good information to be found there. For those that are doing a variety of materials and are interested in other thermal interface applications, if you're interested in some of the steady state capabilities that exist on the market, we are partnered with ZFW. So definitely feel free to reach out for both the transient and the steady state classes of instrumentation. But that all being said, just so we jump into the Q&A here, we'll end the formal session here at this point. Of course, definitely feel free to stay connected with us through our LinkedIn or follow us on some of the content we're doing on our YouTube channel. But all that being said, I'd just like to take a moment to thank you as the audience for joining here today, and also to our guest presenters, Wasif and Bret.